integrals, which are also called antiderivatives. Well, we are just going to work backwards as far as we're basically going to stick with power rule, basic natural log, trig. But let's say that I had 4x plus 8. And the differential dx just means that I'm deriving x as my variable. So basically it's just for notation, nothing for you to get caught up on. So if I want to take the antiderivative, first look at 4x. And here's the rule. The rule is you are going to add 1 to the exponent, so there's understood 1 there. So add 1, so that becomes x squared. We're going to bring down the 4 and divide by that new exponent. So 2 goes into 4, 2, x squared. And notice how if you were to derive it by power rule, 2 times 2, 4, subtract 1, 4x. Same thing here. We are going to, technically there's no variable there, a constant. I'm going to show you this one, and then from now on you can just do the trig. So you can think of it like this. If you add 1, you get x to the first power, and then when you divide by 1, you just get 8. So anytime you have a constant, you can just add your variable to it. Now here's the thing. There's no telling if we had a constant when we derived to get this. So that's why, unless it's a definite integral, you'll always see people put c's, because that means there could have been some constant that you integrated. Well, let's do some more. What about, we'll do some that won't necessarily turn out right or pretty. We'll just give us a strand. So remember the rule. Add 1, divide by the new exponent, and we'll reduce in a minute. Add 1. Oh, I saw what I did. Let's make that a cube. I'm sorry, because we don't want to be able to add them together. So add 1, divide by the new exponent. Add 1, divide by the new exponent. Add 1, divide by the new exponent. A constant, add your x. And remember, there could have been a constant, so plus c. And actually, none of that reduces. It's awful ugly, but none of that reduces, so we're good. Well, let's say I had something like square root of x. Oh, I forgot to put my dx on there. Sorry. Let's say I had something like square root of x. I know you're like, oh, you had to go there. Well, remember, make it a power. And then now is where your elementary math comes in handy, or you can be lazy and do it on a calculator. Some of this, if we were in class, I might shame you for, but because it's usually not too bad. But, so just like up here, add 1. So a half plus 1, 3 halves. Now, if you divide by 3 over 2, that's the same thing as multiplying by 2 thirds. And then bring that down, plus c. Just like, let's say if I had 6, we'll see what happens, cube root of x. Same thing, make it a power, so 1/3. All right, so we're going to add 1, so 4/3, divide by the new exponent, which is multiply by the reciprocal, and then, of course, you got your plus c, but this we can reduce a little bit. 2 goes in there, so 9 over 2. You could have gotten there by 18 divided by 4, which still would have got you the same thing. You also, as far as, let's say, if you had 9 over x squared, Remember, that's the same thing as x to the negative 2. So then you could add 1, divide by the new exponent. So there you go. Now what about, let's say, if I did this? Derivative of 7 over x. Well, notice how if I try to bring that up, you get x to the negative 1. So if you add 1, you get x to the 0 power divided by 0. So it's like, whoa, back the truck up. Something is wrong here. Well, remember, 1 over x is natural log. So that's just 7 natural log of x plus your constant. So now you remember that, oh yeah, those. So if I wanted you to integrate e to the x, remember its derivative is the same thing, e to the x. So that's just 2e to the x plus c. Just like if I had 8 sine, remember what derives to give you sine, just like if I said 6 cosine. Well, remember sine derives to give you cosine, so that's just 6 sine. Cosine derives to give you negative sine, so this would have been negative cosine. Because remember, if you're deriving, sine goes to cosine, cosine goes to negative sine. So that's why. Now, last but not least, let me show you some definite integrals. We won't get to it, obviously, this year. Let's get a better sheet of paper. Because of all this COVID, but where it comes into play is something called the fundamental theorem of integral calculus. And if you're curious, I will be posting that later, might even in the next few weeks. But it's where definite integrals comes into play. But let's say I gave you something like 2x plus 5, and I wanted you to integrate it between the values of 1 and 3. Well, first you just ignore this, integrate it like normal. Add 1, divide by the new exponent. Constants, add an x. So what you really have is x squared plus 5x. Well, how you integrate it or evaluate it, you'll see, put a vertical bar, 3, 1. You plug in 3, so 3 squared plus 5 times 3, 24. 1 squared plus 5 times 1, 6. Subtract the 2. And there you go, 18. I won't give you, especially this year, I won't give you weird ones with trig and natural logs and such. But the same purpose applies. But with trig, it does have to be in radians. So that's a little bit different with it. But no matter what, let's say if I gave you negative 5 and 2 of 8x minus 3. Same thing. Add 1, divide by the new exponent. Constants, add an x. So 4x squared minus 3x. So first, plug in 2. Then negative 5. And subtract. So 4 and 4, 16 minus 6, 10. 25 and 4, 100 minus negative 15. So that would be negative 105. Now to give you a preview for those, it's so exciting. I hate that I won't have time to show it to class of 2020. But the reason why it's negative is because more of it is below the x-axis than above it. And we don't have any time to talk about that with fundamental rule of integral calculus. It just sounds exciting, doesn't it? But for today, I better shut off with that. And sadly, that is the last new topic for the class of 2020. Wishing you the best, and hopefully we will be able to get the virus stuff cleaned up in graduation soon. Have a great day.